Let's explore a few of the features of the fish model. First off, we can look and see that we've graphed both the fish mass in blue and the take here in red. Note that when I click on the graphs in Excel, it highlights them as to what is being plotted. So we have in pink the horizontal axis days, and in blue there's the vertical axis take. Same with Q, or fish mass. We've run the simulation for 2 years. We can see that number of days here on the bottom. If we wanted to plot something besides fish mass, let's say we wanted to plot the natural loss because it's changing, we could just click and drag the box over. Note that it's plotting it on the right hand axis, which is in this case fixed, not dynamic. If I double click on the axis, change my maximum to automatic, we can see now that the natural loss is here. If we could change our major units, minor units, so that we can see for now. So we are using two axes. The red is on the left hand axis, fish is on the right hand side. A good practice is to color code your graphs if you're using multiple axes so they correspond to the labels for those axes. Alright, so now we can start to ask ourselves questions and also be trying to verify our model, meaning we're trying to make sure that it's performing as we expect it would. The first thing we may want to test is to see if it is sensitive to effort. So effort was F, that's 8 in our initial value here, and let's just note our graph values. Let's look at the ending values after 2 years. So basically we have about almost 1,300 grams per square meter of fish, and our take, which is on the left hand axis. But if we put the cursor on the graph itself, we can see that it highlights the value. It's 2.02 grams per square meter per day at the end of 2 years. Let's assume that the effort declined. Instead of having 8 labor hours, we had 6. All the calculations are done instantaneously, and the new graph is made. Now we can see that instead of having 1,300 grams of fish, we have nearly 1,400 grams. And instead of having 2 grams of take, we have 1.6. Let's look at this in terms of our diagram. We reduced the fishing effort, so that means our take should be less, which if we have a less take, that means our storage should go up. We're taking less out. So therefore, the fish mass should have gone up with less effort. If we were to zero out fishing effort, we'll see that we're going to have a lot more fish. So let's do that. Our take goes to 0 because we're not taking any fish. Our fish mass goes off the charts. If we wanted to see what that value was, we can see that it's approaching 1,800 grams. So without any fishing effort, we would have that much fish after 2 years. Let's return that back to 8, which is our original value. One thing we may notice is that the graphs are not actually flattening out like we would like. They're not reaching steady state. One of the ways that we can remedy that issue is to have a longer time step so that we're actually simulating a longer period of time. So instead of doing 1 day, let's do 2 days for a time step. And we notice in the graphs that they do start to flatten out. And there's very little change in the last several hundred days. We also note that instead of simulating just 2 years, we're now simulating 4 years. So the amount of time that we're simulating has doubled. But it's nice to see that what the steady state value can be in this situation. Let's do one more change. What if our supply of fish was decimated, so that instead of having 12 metric tons, we only had 6 metric tons. So we can change E to 6. So, referring back to our diagram, what should we expect to happen? Less fish coming in because we have less supply. We cut it in half. Therefore, less input should mean that we have less stock. That's also going to affect our ability to take fish. So our take should go down indirectly because we have less fish being supplied. If we look at our graph, we can see that yes, our fish mass has gone from 1,300 grams down to about 650 grams. It's been cut in half because the supply was cut in half. And our take now is just above 1 gram, whereas before it was at 2 grams. For this final part of the lesson, we want to contrast changes in initial conditions or initial values versus recalibrating the model. So first thing we'll do is return E back to 12 metric tons, which is our initial value. We'll leave the time step at 2 days since that shows us the steady state value. Model, the simulations assuming that those conditions, the relationships between fishing effort and the source of fish and the loss of fish through emigration don't change throughout the simulation. But we might have a situation where we think that we do need to recalibrate the model. So an example could be maybe we're going to be slightly more efficient with our fishing effort. Right now, currently in terms of efficiency, K3 is the relationship between the take, J3, and the effort and the amount of fish that we have. And this value is 0.0002 per labor hour per day. Or we could look at the diagram and say basically when we have an effort of 10 and a population of 1,000 grams, we're taking 2. What if we were able to take slightly more, let's say 2.5 rather than the 2? This should change our K3 value, and it did. This is basically assuming that we're a little bit more efficient, 0.5 out of 2 or 25% more efficient to take. Well, what did that do to the simulation? It changes K3, therefore it's going to change the take because it's in the equation. And that's going to change the DQ, the change, which then ultimately is going to affect Q. And we can see that when we change that, before we were having a fish mass of 1,300 grams. Now we're a little more efficient. We're taking more fish for the same effort. Notice that we didn't change the initial values in this situation. So we reduced that by 100 grams, and our take has gone up now to 2.4, whereas before it was at 2. The recalibration that's related to believing that our efforts are more efficient. We also could have changed the recalibration differently. Let's return it back to 2. Well, there are 3 variables that involved in K3. There's J3, the flow, or the take. There's the fish population Q, and there's the effort F. Changing any one of those is going to change K3. Let's say that for the given effort of 10, it's 2. But if we also want to think, well, we don't have as many boats and we're still going to catch as many fish, that's also an increase in efficiency. So instead of having 10 labor hours, let's say that we only needed 8. We're still only taking 2 in this calibration, but by changing F to 8, we've also increased the efficiency by 25%, so that our new value for K3 is 0.00025, which is identical to the change in terms of values for K3 that we saw by changing J3 to 2.5. Let's change that back. We also could think that maybe there's more emigration. Maybe it's sped up for some reason or increased its rate. So instead of it being 3 when the fish population is 1,000, we'll think now that it's 4. Let's change the value of K2 from 0.003 now to 0.004. And again, we can see that that's going to affect our fish mass after 2 years or after 4 years of simulation, as well as our take. Now, one thing we want to be careful about, let's change J2 back to its 3 value. We need to be careful with our recalibration and changing these values, because we can see that a parameter like Q is actually tied to 2 pathways. It's tied to the natural loss, K2Q, and it's also tied to the take through K3QF. If we were to change Q, instead of it being 1,000, maybe 800, that's going to change K2 and K3. If that's what you wanted to do, maybe that would be a recalibration based on realizing that the population was slightly smaller than you originally thought, but the immigration, the emigration, and the take were all the same, so that change would be valid. However, if you're just trying to change the natural loss or the take by themselves, then changing Q is not a good technique, because you'll have other effects in the model. Let's change that back. One last thing to note is that the actual fish that we landed or could sell is not stipulated in this model, because the model is just focused on the population of fish Q and how much we take from it, not how much we land. We would need a 4th term for that pathway. It would be K4QF, and we could add that to our model to keep track of it, but we should realize that it doesn't become part of the differential equation for Q, although it could be a flow that we are interested in tracking. So we've explored the model fish in the Excel simulation. The next lesson, we'll explore adding a second tank and autocatalytic feedback.